Excellent. We're going to get started. Before we get into our activity for today on section 7.1, I've got a short survey for you guys. I'm going to drop the link for into the chat. So now we are going to get started with our activity for today, which will be a Desmos activity. So I need to go there. Sorry, I'll share my screen momentarily. All right, so here is the link to the Desmos activity. Yeah, if you click on that, it'll drop you into the activity for this class period. If you already registered, the first time we did a Desmos activity for the couple weeks ago, I think, into the class, you should just be able to click in and it'll drop you in the activity. If you haven't, you'll have to put in some information, and that's totally fine. Please, once you're in there, answer the first question. It is nothing about math, it's all about how you're doing. So please do that once you're in the activity. So here's what we're going to do. Thank you so much for participating in this and saying how you're feeling. And again, hopefully you guys can start feeling better, feel a little bit less tired. Hopefully things start turning around and it gets more positive. So we'll go for that. Right, so we're going to do the first two questions in one chunk here. So I'm going to open up more stuff. So we're going to open up the slide 2 and 3 of this activity here. They're both card sort activities. All right. The first one, you are matching the vocabulary terms of inference, parameter, sample, and statistic with their correct definition. Right, so you got 4 terms and 4 definitions. Please sort them accordingly as best as you can. In the next one, this is a scenario. A business owner wants to know the average household income for her business zip code. So she randomly samples 80 households in the zip code and finds their mean income. So you need to match the context with the term. So we have parameter, population, statistic, sample, and we have 4 contexts to match with those terms. All right, so please take the next, I'd say 3 minutes to match these bad boys up. If you have any questions, please put them in the chat and let me know. And then we will talk about it in a few minutes. All right, excellent. I think most of us have tried to organize these cards. So first, I will quickly go over slide number 2, matching the term with its definition. All right, so the first one here on my screen, if you're viewing the shared screen, is inference. The inference, right, is an estimation of a characteristic of a population using sample statistics. That is what inference is. It's an estimation of a characteristic based on sample statistics. A parameter, remember parameter goes with population. So that means a parameter is a number that describes some characteristic of the population. Sample is a subset of a larger population. So the sample, like a simple random sample, is a selection of the population that we're getting data from. It's not the entire population, so it's a subset. And a statistic is a number that describes some characteristic of a sample. Remember, statistic, sample. Right? Is there anything I can clarify about this question? Right. We move on to slide number 3. We have parameter, population, statistic, and sample. All right. Can someone tell me what is the parameter? type it in the chat if you like, or you can just shout it out from your mic. You can see there's a good chunk of you that have this correct. At least there's 1, 2, 3, 4, 5, 6. Mean income of all households in zip codes. Yes, it's the mean, right? And the giveaway is it's for all households in the zip code. That's the entire population. And the notation of mu. Remember, mu goes along with the parameter, right? Mu is the mean for the whole population. Thank you, Brittany. All right. And then what is the population? Yes. All households in the zip code. Thank you again, Brittany. So we have statistic and sample. Right. And we'll do this one. The statistic is X bar, the mean income of the sample. And the sample is the 80 households surveyed. So we're moving on to screen number 4. This is sampling distributions. This one has a fun little simulation. All right, sampling distribution is the distribution of statistics from all possible samples of the same size from a population. Please note, right, sampling distributions are made of statistics, means, proportions, quartiles, etc. Sampling distribution simulation here. This simulation estimates and plots the sampling distribution of various statistics. You specify the population distribution, sample size, and statistic. An animated sample from the population is shown and the statistic is plotted. This can be repeated to estimate the sampling distribution. So we're going to take a look at this guy. So we have this sampling distribution simulation. There's lots of instructions. You can read through that if you like at some other point in time. We're going to begin our simulation. So on this simulation, we have 4 different setups for a histogram. This first one here is our parent population. It is approximately normal. Right? I could change this and go uniform, skewed, make it my own. We're going to stick with normal for now. Right? And here represents a single sample set. In this case, my samples, I'm going to run 5 samples, right? Or at least I'm taking 5 samples, and then my distribution, my mean from this sample of 5 drops in here. I can take 5 more. I get a new mean of the sample, right, X bar, and that drops in here. We'll take 5 more samples, right, so my sample size is 5, right, and we go in through here. This is showing a sample size of 5. I can change my sample size to 25. And you can see it's starting to fill in the sample data distribution. Once all 25 are done, it drops in 1 X bar, 1 mean. Right? We can run it again. So again, this second histogram is only showing my sample data. Right? It's the distribution of the sample set. And I get a mean. It goes again. We can speed this up and be like, okay, cool. let's do 10,000 simulations of 25, of a sample size 25, and we get this distribution. Right. Let's do this. Let's compare. Let's say we do a sample size of 10 versus a sample size of 25. And let's run 100,000 simulations. We get two slightly different histograms. They're both approximately normal. One has a little more variation than the other. One is more varied, has a larger variance and a smaller sample size. Larger sample size on the fourth one, smaller variance. We can see though the mean and median for both of these is almost identical. Okay. Which means we most likely have an unbiased estimator for both. So this is kind of fun. We can play around with how this is done, right? And it gives us a nice simulation of how this works out, right? An actual, like, we can run our own simulations based on different data, right? I can play around with this bad boy if I want. We can make a custom one, right? So we have this. That's fun. We can play with that. I'll have this linked in Canvas at some point today, so we can play with that more if you like. But for now, let us answer this question. What do you notice and what do you wonder about this sampling distribution simulation? All right, now I know that wasn't enough time for everyone to answer what you notice and what you wonder. And that's okay. If you got to it, excellent. If not, it's okay too. So I saw a couple of cool noticings and wonderings. So one wonder that I'd like to address from one of the students is that they wonder what the point of sampling is if it's not always accurate. This is an excellent question, right? Why do we bother to sample if we're not 100% convinced that we're getting an accurate result? Practically, like a practical answer is that sometimes that's the best we can do, is get something that is reasonable and close to what the actual value might be, but we may not ever know the actual value. It might be impossible to attain. We might not be able to get responses from everyone in the population. So the best way we can do is sample and use that to estimate what it could be. That's kind of the basis of statistics, is it gives us a good idea of what should be, or what people are thinking, or what value is reasonable, things like that. But there's no guarantee that it will be perfect and it will be accurate to what the actual value is. That's why we have these different measures and inferences and things to help give us confidence in our results. You know, we'll learn some other techniques later in the course that help give us more confidence in what we're doing. But unfortunately, sometimes sampling is the best we can do. But it's a really, really good question, a really good noticing. So yeah, I wanted to address that. I thought that was an excellent question and just a fun one to answer. So the couple other things, I wonder how the simulation makes such an accurate response. So part of the reason we're doing sampling distributions, right, is that it will essentially provide us with a more reasonable thing to work with, right? If all that I did, right, if we run this animation here, is rely on a single sample, right? Every sample is too varied to give me something that might be accurate. But if I run a lot of samples, right, that's going to provide me, I run a lot of samples and I take a single statistic from each sample to use as the, like as my statistic, right? The mean, the median, a specific quartile, standard deviation, something like that. I can get a more accurate reading, right? Because I'm taking just a single reading from an entire sample and collecting all of those. So it gives me something that's a little more reliable than just one massive sample. Yeah, so is that. Anyhow, hopefully some of these other wonderings we'll be able to answer throughout the rest of this course and the rest of this chapter. But yeah, thank you for that. So now we're going to move to the next couple things here. So I'm going to do the next two problems here. All right. So we have a sample or sampling, and then accuracy versus precision. So we're going to answer these two slides next. Sample or sampling, please, in this box, write what a sample distribution is and what a sampling distribution is. We have an example graphic here to kind of show visually what they are. But we're kind of looking for, in your own words, what's the definition? What's a sample distribution? What is a sampling distribution? How are they the same or how are they different? And then in the next one, accuracy versus precision, we're answering the question, how do you avoid bias and how do you reduce variability? And again, we have a visual to help aid in your response here. And please, in this, only just one idea for each part. One idea of how to avoid bias, one idea for how to reduce variability. All right. So we'll be working on answering these two questions in the next chunk of time. Alrighty, so we're going to go over these real quick. So if we want to move back to the sample or sampling screen, so if you're on the second one, the accuracy versus precision, please move back to sample or sampling. So a sample distribution. I saw a lot of pretty good responses. So the main thing, right, is that a sample distribution is providing us like the distribution of the values of a variable for individuals in the sample. Okay, so it's like if I did a sample set of 20 students, the histogram or dot plot would show the values I collected from each of those 20 students. A sampling distribution shows the statistic values from all the possible samples of the same size from the population. Okay, so the sampling distribution, if I did sample sizes of 20 students, would be if I went to Orange Glen and I sampled every possible selection of 20 students on campus, and maybe I was doing the mean height. So then my sampling distribution would record the mean of each of those 20 students, right? Those 20 student samples. Also keep in mind, sampling distribution could record any statistic that you're recording, value that you're recording from your sample. It could be the height, the mean height. It could be the median height. It could be the standard deviation of everyone's height. It could be the proportion of students who are taller than 6 feet. And it just depends on what you're collecting data on, what you're interested in knowing. Right? Is there anything I can clarify between those two terms? Okay. And then for accuracy versus precision, right? One way to avoid bias is to sample randomly. Right? Make sure you're doing a simple random sample so that you're not inherently selecting a biased section of people or individuals or things, right? You want to sample randomly. That's just one way to avoid bias. There's other ways to avoid bias you could have listed. And then how do you reduce variability? Have a larger sample size. Okay. So if you increase your sample size, you're going to reduce the variability. Those two things are inversely related. And this is from what we saw yesterday in class. Right? As the sample size increases, variability decreases. So that's one way I can reduce variability. We just need to be mindful that we don't violate the 10% condition, and our sample size should not be larger than 10% of the population we're sampling. Okay. Is there anything I can clarify for this one? All right. So then we're going to move it on. We're going to jump to the next two screens. So we have two different contexts, one on each screen. Each of them follow these same directions. Each boldface number in the context below is the value of either a parameter having to do with the population or a statistic having to do with a sample. Choose which each number is, and then select the appropriate notation to describe the number. So we've got our context below. Once you've read the context, you're going to select one checkbox that correctly pairs the parameter with its variable and value. Right? There's four choices: parameter, 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 parameter. I've got them set to shuffle, so they might not be in the same order as on my screen here. All right. So you're going to select the parameter that has the correct variable and value. Then you're going to select one checkbox that correctly pairs the statistic with its variable and value. So you'll have two checkboxes selected for each of these next two screens. All right. Then the New York to Denver, same directions, different context, and the variables are different. So take the next 3 minutes, right, and make your choices. And again, this is not necessarily about getting it correct right away. It's about trying. Right? We'll talk about it so that you can understand it. Excellent. All right. So real quick, let's talk about these. Our first example, we have the Arizona iced tea. On Tuesday, the bottles of Arizona iced tea filled in a plant were supposed to contain an average of 20 ounces of iced tea. Quality control inspector sampled 50 bottles at random from the day's production. These bottles contain an average of 19.6 ounces of iced tea. Right. For this context, right, the parameter, right, will have the variable mu, and that is 20 ounces. That is supposedly the actual mean for the ounces. The statistic should have the variable x bar, and in this sample, the x bar, the mean for the ounces, was 19.6. Okay, so those are the two boxes that should have been selected. Then if we go to the New York to Denver, on a New York to Denver flight, 8% of the 125 passengers were selected for a random security screening before boarding. According to the TSA, 10% of the passengers at this airport are chosen from a random screening. In this case, the parameter should have the variable p, and if it's the actual value, it should be at 10%. So we have parameter p equals 0.10, or 10% of passengers. The statistic should have the variable p hat, right? The p with the little hat on it. And that should be 8%, or 0.08, because that's what we actually had in that sample of 125 passengers. Right, so we have statistic is p hat equals 0.08, or 8% of the sample passengers. Is there anything I can explain or clarify for these two examples? So then, excuse me. We're going to move on to the last part of this. So I'm opening the last 3 screens right for this. So please scooch it on over there. And what we're going to do is I'm actually going to put you guys, let's see, we're at 11:40. All right, this is going to go quick. All right. I'm going to put you guys in breakout rooms for 5 minutes to just discuss these problems, and we'll come back and go over the solutions. All right. I'm putting you in rooms with 6 people in the hopes that with more people in the room, there will be more people who want to participate in each room. So please actually have a discussion, talk about the problems, and discuss what you think the answers could be. Try not to spend too much time on each problem. Don't worry about typing in your answers right now. Just talk about the problems and what you think the answers are. That will be enough. Right? All right, well, welcome back to the main room. So I know that wasn't enough time to accomplish all of these problems. Hopefully you guys actually talked in your breakout rooms. I know nothing happened in the chats because I was watching to see if anything happened in the chats. So hopefully you guys talk to each other. If not, you're missing out on an opportunity to learn from your classmates. All right, so for the first problem here, all right, the individuals, those are the M&Ms. Those are the individuals participating in our study, M&Ms. The variable is color. We're keeping track of the color of the M&Ms in our sample, so that becomes the variable. And the parameter of interest is proportion of orange M&Ms. All right. That is what each of these things are. The parameter of interest is proportion. That's what we're keeping. That's what we're really interested in. What is the proportion of our total in the sample? That is orange. Next part here, which of the graphs that follow could be the approximate sampling distribution? This is the key part, sampling distribution of the statistic. The first one is not a sampling distribution. It is a bar graph displaying the frequency of each color. All right, that is from a single sample of 50 M&Ms. It's these other 2 graphs are sampling distributions of the proportion of orange M&Ms. So that means they took like this sample here and said, okay, this sample had 10 orange M&Ms out of 50, right? So they get a 10 at 1/5, 0.2, right? So the p hat for this sample was 0.2, so that created a dot on here, right? So between these 2, we're trying to decide which one is probably the one that resulted from our sampling. I know it's hard to see, the numbers are tiny. The middle one here has a mean or median that is right around 0.2, so that is going to be the most appropriate or approximate sampling distribution for the statistic of proportion of orange M&Ms. Lastly, for the last question here, we have these histograms of the values taken by 3 sample statistics and several hundred samples from the same population. The true value of the population parameter is marked on each histogram. So the arrow underneath each histogram is showing the true value. Right, which statistic has the largest bias among these 3? That's going to be histogram C, because it is easy to see that the median or mean of C is to the left of the true value. Its accuracy is way off. The other two, their accuracy is still pretty good. One's more variable than the other, but they're pretty well aligned to the true value. Right, which statistic has the lowest variability? That's going to be A. It has the least variability, right? It's the most slender. And then based on the performance of the three statistics in many samples, which is preferred as an estimate of the parameter, that again is going to be A, because A has the least variability and the least bias. Right? And think of it as that bullseye, right? It's the most closely clustered over the bullseye sample. All right. Is there anything I can clarify? So again, thank you guys for participating. I know that we're just a little bit past an hour. I do apologize about that. I wanted to make sure we got through these examples to help really make more sense of this new vocabulary. But that is the end of our lesson and time for today. I do encourage you, please look at the practice problems for 7.1 in Canvas so you can get a little extra practice in. Other than that, have a great rest of your week. I'll see you guys on Tuesday next week, right? So have a great weekend as well. And we'll see you later. If there's anything I can help you with between now and then, please email me, let me know.